Good morning. We're this close to reading break. We can do it. Okay, so as I suspected, I slipped a little bit behind. It's okay. We're just gonna take the rest of this week to finish chapter 4, which was the old chapter 3. So I get confused sometimes. I was hoping to get into chapter 5, but I think it's nice if we just start a fresh chapter after reading break. Okay, and then quiz 2 is going to be on chapter 4 and 5. Okay, and so this week we will just focus on finishing chapter 4. We will finish chapter 4 and start chapter 5 after reading break. And start chapter 5 after reading break. All right, no school next week. In case you didn't know, I can't remember if it was this class or one of my other classes where someone didn't know when reading break was, and that's crazy. You have a whole week off, a whole week to kind of get organized and get on top of things. I know it, not as much as you hope is going to get done, but at least some of it will get done. And then so quiz number 2. We'll cover chapter 4 or chapters 4 and 5. Oops. Okay. Off the top of my head, I can't remember how long it takes me to talk about chapter 5. So, but I have a long list of things I need to do over reading break as well. So one of those things is mapping out the quizzes. I suspect that it would be the second Friday coming back, but I don't want to commit to anything quite yet. Oh, question, maybe. Or maybe accidentally unmuted. I'll do you a favor. It's everyone's worst nightmare to be accidentally unmuted. Don't worry, nothing happened. I could just hear like little shifting of papers. So that's when I'm like, hey, is there a question out there? Good. Okay, so quiz 2 is going to focus on chapters 4 and 5. So far, we've only seen chapter 4, and just like before, the assignments, and maybe I'll say use the assignments. Gonna keep bumping this over here. Use the assignments for practice. Okay. Okay. So that's kind of where we're headed right now. Well, okay, so I got a direct message, but it was about the adjustments. So I think that concerns everyone. So would you mind sending it to everyone instead? And then then everyone can see what the question is, because it's quite long, so I don't want to. But I adjusted quiz 1, and I always look through and make adjustments. Thank you. I always look through and make adjustments if I think it's necessary. Right, if the quiz is too long, or if no one got 100%, then I scale it back, right? And so how I want you to look at it is the grade that you get immediately after you finish the quiz. That's kind of the lowest possible grade. And then what I want you to do is I want you to look back against the work that you did and make sure that you're not missing any marks, and then let me know. So I'm going to leave it for the next few quizzes. I'm going to leave it to you to figure out, okay, I had that in my written work, so now I'm going to go and then you ask me to go back and look, and then I can make adjustments. So that's what I meant by I will make adjustments, but I won't look through everyone's quizzes. I look through for rounding and stuff, but not your written work unless you ask me to. Okay. So good. All right. So let's do a little bit of review. I think that was all the things I wanted to do. I'll post an assignment for this week, and that'll be part of your chapter 4 assignments, of course, that you'll have reading break to do. So I'll give you until the end of reading break. Okay. Okay, so a little bit of review. We said that we can have a binomial distribution. A binomial distribution, and how I want you to read that is just like a binomial type question. Okay, so it's going to be your job to read all these questions and figure out now, do I have, for example, a Z-score question, or do I have a binomial question, right? And so that's going to be the hardest part, I think, especially when we're just starting out, right, is reading the question and figuring out what type of problem do I have. Okay, so for a Z distribution, right, or for a Z question, you would have to have the mean and the standard deviation. So those would be given to you. And then you would be asked to find probabilities associated with some outcomes, right? Or potentially find the outcome based off of the probability, right? We can go either direction. For binomial distribution, what you're looking for is you have to have only 2 possible outcomes, right? And we said last day, okay, well, sometimes we can kind of force that to be true, right? If we look at letter grades, and I'm only interested in people who get an A, let's focus on the positive here, right? Get an A, then I can say that, okay, that's going to be considered a success, and anyone who doesn't get an A is going to be considered a failure. Okay. Now, the success terminology usually means something bad, right? It's usually the bad things that we're trying to model and trying to figure out when they happen, right? So that we can prevent them, right? People dying from a disease, for example, would be considered a success because that's what you're interested in, but that's not a success as we know it, right? So just keep that in mind. So a binomial distribution, what are we looking for? Well, it can only have 2 possible outcomes. Right, so usually we code those as 0, 1 outcomes, or you can think of them as success, failure outcomes. Okay. And then what was the other condition? We have to have an independent probability of each outcome. It doesn't have to be 50-50. In fact, it's usually not, right? Except when we flip a coin, for example, then it's a 50-50 probability, right? But each outcome has the same probability, or each outcome has a fixed probability, Okay. Where P is the probability of success. Oops. And Q, which is 1 minus P, is the probability of failure. Okay. So, all right. We spent quite a bit of time working up to the formula, right? And this is not something that you're expected to remember, right? In fact, it's on that formula sheet that I posted. We don't follow it directly, but it's nice to have some of these formulas kind of laid out. For example, I don't think we went back and we looked at of course, the Z-score formulas and the X formulas are on here. Can't remember if I grabbed those or not, but here, this is for the binomial distribution. Right. So here we can have the probability that X equals K successes. And I'm just going to rewrite this formula with Q here. That's the only difference. So if you're okay with this, but also I want to give you the chance to write it out. So I figured I may as well write it out with you. So the probability that X equals K is N choose K, right? How many ways can I have K successes in N trials, right? And so that's terminology from last day. And so N trials, K successes, if P is the probability of success, I need to have K successes, so P to the power of K. And then I need N minus K failures then, right? So Q, which is the probability of failure, to the power of N minus K. Okay. We also said that the mean and the standard deviation of, and we didn't really introduce this notation, B stands for the binomial distribution. And the only things that we need in order to determine the binomial distribution and to do these calculations for any K, right, is we need N and we need P, right? And so for any calculation of X equal to K, we need to know, or the probability of X equal to K, let's say, we need to know N and P. N is the number of trials. Oops. And P is the probability of success. If I have the probability of success, then I can find the probability of failure because there are only two possible outcomes, right? And so what we said was, I can actually find a mean for this binomial. I can find the expected number of successes, right? Because we're interested in successes. Or rather, that's how we pick what is a success. It is the thing that we're interested in, right? So then the mean is the expected number of successes. And then we can also find the standard deviation, which is the square root of NPQ. We're going to parking lot that for just a little bit while we do this example. And then we're going to bring that back up. And what we're going to see is we're going to see this link between a binomial distribution turning into a normal distribution. And I know that's crazy, but I'll show you when and how it works. Okay, but first let's do this example. So let's see where this page break is. Oh, right there. Let's put it on a fresh page. How about? And I'm going to crop top this. Crop. Okay. So you might have heard of the S&P 500 index. It's stock related, so you have definitely heard about it. But here in this fake scenario, right, we're going to say that the S&P 500 index has a probability 0.56 of increasing in any week. Okay? And then assume the change in the index in any given week is not influenced by whether it rose or fell in the previous week. That's not true, right? But why am I saying that? Well, that's what makes these probabilities, that 0.56, that's what makes it independent, right? And so now we have these fixed probabilities for each week, right? And so here we have the probability, and maybe I'll use green, of increasing in any week. Okay? And maybe what I'll, before we start answering these questions, I'll even go a little bit further back there. So now I have P must be 0.56. Okay. It also tells me what a success is, right? It says that, okay, if 0.56 is the probability of increasing in any week, right, then the success that we're interested in is an increase in a week. So therefore, the success is an increase in a given week. How would this be changed if I said, okay, now you're interested in the number of, or the probability of it decreasing or staying the same in a week? That would be the same problem, right? Except now P would be 1 minus 0.56, right? So it depends on what the success is, but often if we're given a probability and we're told that that probability is of it increasing in any week, then we know that that means that that's a success. Okay? And so here, when we say this, this is totally unreasonable, right? So not realistic, right? Saying that, okay, no matter what happened last week, the probability of it increasing stays the same, right? It's always 0.56. You start a fresh week, you get a 0.56 probability of increasing, right? That's not realistic, but it makes the probability fixed, right, for each week. And maybe I'll say that for each week. Okay. So now I'm told to let X be the number of weeks among the next 5 weeks. So I have 5 trials, right? I'm going to look at 5 weeks. So in the first week, did it go up or did it not? Right? Notice how it can go up, it can go down, or it can stay the same. Okay. And so the options are increasing, decreasing, or staying the same. You don't want to forget about that one. But what are we saying? Well, if this is a success, then these must be failures. Doesn't matter if it stayed the same or it decreased, that they're both failures. Okay. So we've made this binomial situation. Okay. And so now we want to find, so let X be the number of weeks among the next 5 weeks in which the index rises. So now we're ready to tackle these problems, but there's a lot of information here just in the question, right? And so I think already you can imagine what these questions are going to be like. This first one's fairly hand-holdy. Let's see here, which throws me off sometimes. Okay. Let's put it there. how many possible outcomes are there in each week? Okay. And so this is kind of referring to what we just said here, right? But what we're going to say is, well, there are two options. There are two outcomes, right? Increasing or not increasing. Okay. So since we have this fixed probability for each week and two possible outcomes, right? That's what means we have a binomial situation. Okay. And I can't remember if it's part of the question. So I'll add it here, and if it is, I'll adjust it. But therefore, with only two possible outcomes, and fixed probabilities, this is a binomial question. Okay. Oh yeah, because we're only interested in, so let X be the number of weeks among the next 5 weeks in which the index rises. And so then we have our success. So even though decreasing and staying the same are both options, right? We can lump that into one option and say, well, that's just not not increasing, right? And so here, I'll add that here. So this is not increasing. So when we talk about the two options, right? It can increase or it could not increase, which actually wraps up these two options, right? It decreasing or staying the same. But because that's not what we're interested in, we just lump those together as failures. Good. Okay. So we have this binomial question. And let me. And we already know what this is. Right? So usually all these parts are a lot easier than you think they're going to be. That's what I get questions about. People have done all this work and then they go back and they try to answer these little bitty questions, and it's a little bit weird to kind of think that we would ask such a simple question. But a success in this case is it increasing, right? So a success, we said already, is the index increasing. Clean that up a bit. And let's see if I can. Put another one on here. So what are N and P? Well, we already found them, right? When we dissected the question. So all of these are just in the question so far. We said N was 5, right? We're going to look at 5 weeks. And P was 0.56, the probability of increasing, which is a success. Okay. Nice. Now for the tricky part. what are the possible values of X, right? It could increase in all of the 5 weeks or 4 weeks or 3 weeks or 2 weeks or 1 week or none of the weeks, right? That's the tricky part, is remembering that, okay, it's possible that it didn't increase in any of the weeks, right? And so X can be 5, 4, 3, 2, 1, or 0. We often forget about the 0 option. That's like the most common error that I see when people do these problems, is they forget that 0 is also an option, right? That's just decreasing in 5 weeks, right? So good. Or staying the same, decreasing or staying the same. I should say not increasing in the 5 weeks. This is when we don't see an increase in the 5 weeks. Okay, just to clarify, because that can totally happen, right? So, so we need to take that into account. Okay, good. What is the probability of the index increasing in more than 3, not including 3 of the weeks? Okay, just to clarify that, I mean more than 3, which excludes 3 itself. Okay. So if we look at our options, right, if we focus on, okay, we said that X can be 5, 4, 3, 2, 1, 0, right? So now you'll see why it's so important to remember the 0 option. What I'm going to do is I'm going to, kind of highlight, or I'll circle the ones where that satisfy the criteria that we're trying to solve for. Okay, so in more than 3, so that's going to be 4 or 5. So I know how to find exact probabilities using the formula, right? 4 or 5 means that I'm going to have to add those together. Okay. And so what we're going to find is that, and maybe we need to calculate these exact probabilities individually. And then what we're going to find is we're going to find the probability of, and what I'm going to do is I'm going to translate this question into an inequality with respect to X, right? So X is the number of weeks that it's increasing, right? In more than 3, not including 3, so X greater than 3. Okay. Is what? Is the probability that X equals 4 plus the probability that X equals 5. What you're going to see is that I often get lazy, and usually I don't write the X equals 4 because it's implied from the question. So sometimes I get lazy or I'll say even often, I get lazy and just write the probability of 4. And you're going to see why in a second, because if you're doing, if you're trying to find, 4 of these probabilities, then you develop some shorthand, right? And so what we're going to need to do is we're going to need to develop or calculate these exact probabilities individually, okay? And so usually what I do, I write out the general formula that I'm going to fill in, and then I'll calculate the individual probabilities, and then I bring them back into the formula. Okay, so what I'm going to do is I'm going to remind myself that in general, the probability that x equals k is n choose k times p to the k times q to the n minus k. K changes for each of these, right? So I'm going to have to do it for k equals 4 and then for k equals 5, right? But n stays the same because I'm looking at 5 weeks, and that doesn't change, right? P doesn't change and Q doesn't change, right? So let's just make a note here that Q is 1 minus 0.56, which is, and I don't like it when you write across the equal signs across the page, so I shouldn't. But let me confirm. There's my trusty calculator. 1 minus 0.56 is indeed 0.44. So Q is 0.44. So once you've shown that, you can just use it, right? Okay, so let's see here. All right. So the probability that x equals 4 is 5 choose 4 times 0.56 to the power of 4 times 0.44 to the power of 5 minus 4, which I'm just going to cut to the chase here and say it's 1. Okay. So I'm going to go to our calculator and I'm going to find these values. Remember how we found the choose function, NCR, and I want the 5 choose 4, which is 5. What if I just keep going, right? Times 0.56 to the power of 4. Now, what's important if you're using this app is you have to step down the bracket. I call it stepping down, but so you can use the arrow to the right, which would step it back down so you're not working in the exponent anymore, or you can just tap outside of the bracket and then close it, and then times 0.44 to the power of 1 is just 0.44. Okay. So I'm going to just jot that down so I can transfer it 0.216358912. Now I will copy it in, but I'm going to do it for the 5 as well. So that's why I'm holding off. So this becomes 0.216358912. And it's totally fine. In fact, you'll probably just end up skipping straight to the answer, and that's fine, because sometimes you'll just want to keep going in your calculator. That's the easiest and probably the best way to do it anyways. So that's fine to skip from just stating the formula to going to the answer in this case. So the probability that x equals 5 is my next stop. right? And so here, if x equals 5, well, then I have 5 choose 5, 0.56 to the power of 5 times 0.44 to the power of 0. Anything to the power of 0 is 1, remember? But if we're using the calculator, it'll just do that for us, right? So maybe we'll show it here. So next calculation, first I'm going to start with 5 choose 5, end bracket. So I got a question. Are you allowed to calculate the choose function using factorials? Yes, of course. But I mean, unless you're really, really comfortable with factorials and canceling, some of these can get really crazy. So however you find the choose function, if you use the factorial formula, that's totally fine. But like I said, you'll probably need a calculator at some point, right? Because sometimes they won't cancel nicely, right? There's tricks to working with factorials. So, but you're more than welcome to do it if you want to. 0.56 to the power of 5, end bracket. And then just for completeness sake, 0.44 to the power of 0, which we know is times 1, but it's just so I can have it in my screenshot here. Done. Save to photos. So many photos. I should probably delete a lot of them. And crop it up. Sure. Oh. So I can keep it on the same page here. Right. This is 0.05507317776. Okay. So if we go back to what we were trying to solve, and that can be a problem, right, with these problems, is because we feel like we did so much work here that surely we're done, and you might have even forgotten what the original question was. So always go back and make sure that you've actually answered the question, right? And so to find the probability that x is greater than 3, we have the probability of 4 plus the probability of 5. So getting a little bit sloppy here, but I think you're kind of keeping up, hopefully. And so this is going to be, and let me try to make just one more line of room here. How can I do that? Oh, not by doing that. How about if I bump that up and bump this up, bump it up. So that's going to be both of these added together, which is 0.216358912 plus 0.05507317776. You can see how it's so important that you keep all these decimal places, right? Especially if you rounded the second one, right? What if you rounded it to 1 decimal place? That's nuts. Don't do that. Right? But rounding to 1 decimal place, this would be 0.1, which would change the total probability significantly, right? And so we don't want to do that. You want to keep all your decimal places. And this becomes, let's see if I can use these values. I have the previous answer button plus, and how can I use the previous answer? Wonder if I can store this somehow. Copy. Can I do this? Cannot paste it. Okay, fine. I gave up. I'm just going to do it on my calculator because otherwise I have to write it down. So 0.216358912. I think I got it. Who knows? 0.05507317776. 0.2714320896. I'm counting on you guys to check what I write, because sometimes my typos, I mean, I'm just punching it into my calculator. Sometimes they slip under the radar and can get really confusing when you're looking back over it. And so just if you're following along on your calculator, then let me know if something's wrong, because it happens. Okay, good. So now we know the probability of it increasing in more than 3 weeks, which excludes 3 weeks, is 0.2714320896. Okay, great. Oh, that's not what I wanted. I wanted these questions. Did it again. How about that? Okay, so let's see here. We're gonna find the mean and the standard deviation, but before we do that, what if I wanted to find, let's add a part here. Another example. What's the probability of it increasing in at least 1 week? We're not going to do it. We're just going to set it up. Okay. How would you find the probability of the index increasing in at least 1 week? In at least 1 week. Okay, we'll start and we'll say, okay, how about, I'm just going to bump that down. Let's list all the possible outcomes of X, and we'll start there. So X can be 5, 4, 3, 2, 1, 0. Okay. It's technically a set, but I'm not writing it as a set, although I should, like that. It's a set of numbers, and usually we write them from in increasing order, but sometimes I just like to count down, and then that helps me remember to include the 0 as well. So let's see here. What are the options? Well, at least 1 week. So at least 1 week includes 1 week, right? So it can be 1 week, 2 weeks, 3 weeks, 4 weeks, 5 weeks. Okay. So we can translate this into probability notation, and we can say the probability that X is greater than or equal to 1 is, and now just for kind of nice looking sake, I'm going to write them in increasing order. The probability of 1 plus the probability of 2 plus the probability of 3 plus the probability of 4 plus the probability of 5. So again, you would need to calculate these individual probabilities. And would need to calculate these individual probabilities. First. Let's remember, yeah, exactly. Don't look in the chat. The answer is there, right? What's another way that we can do it? No, do look in the chat, it's good. What's another way that we can do it? I look at this and I say, no way, do I want to do that? No. What's another way that we can do it? Well, these are all the possible outcomes. So if we think back to all possible outcomes, that's the sample space, right? And so the total probabilities must add to 1, right? And so, or we remember that that 5, 4, 3, 2, 1, 0 is the sample space. Therefore, the total probabilities must add to 1. Therefore, the probabilities must add to 1. So then we use that same trick that we used with our tree diagrams, and it's a common trick, right? We use it for the normal distribution. Okay, if I know the area to the left, then I also know the area to the right, right? And it all leverages that the total probability has to be 1, which is a fact. Okay, and so then what we can say is the probability that x is greater than or equal to 1 must be 1 minus all the outcomes that are not greater than or equal to 1, right? And so technically what we're saying here is 1 minus the probability that x is less than 1, right? Which is the complement probability of A is 1 minus the probability of not A, right? The complement of A. So we are leveraging those probability rules, but we don't need to think about them like that anymore. It makes it a little bit easier. 1 minus the probability of 0 in this case, right? But even if you wanted to find the probability of at least 2 weeks, right, then you would have to figure out which one is going to be the least number of calculations, right? 2 weeks would be 2, 3, 4, 5. So I'd rather just take 1 and subtract 0 and 1 instead, right? So what's the probability of 0 weeks? Why not? How about I alter this to ask you to find the probability? Because now, right, it's not that crazy, right? I didn't want you to go in thinking that we were going to do the whole thing, but here we go. Okay, so if I have to find this probability, well, that's going to be 1 minus, and because it's just one calculation here, then I'm just going to do it in line here, but you don't have to. And the probability of 0 is going to be 5 2's, oh, sorry. It's hard not to write it as a fraction sometimes. 520 times 0.56 to the power of 0 times 0.44 to the power of 5. Just going to do it on my calculator here. 520 is 1. There's only one way to choose no increases, right? And that would be not increasing, not increasing, not increasing, not increasing, not. It has to be continuously not increasing. So it makes sense that there's only 1, and then 0.56 to the power of 0 is still just 1. So the one thing that we're actually doing any calculation on is 0.44 to the power of 5. Tried to put 6, nice try. 1 minus 0.01649162224, which is 1 minus, which puts me at 0.9835083776. Oops, sorry. Nice. So you can find those probabilities, and yes, sometimes it does involve a lot of work, right? And sometimes, but for me at least, if I know what I'm doing the same thing over and over and over again, then that almost becomes fun, right? You feel like you know what you're doing, and you just kind of plug through it, and it's tedious, but it's not hard anymore once you figure out what you need to do. Okay. So now let's find the mean and the standard deviation of this distribution. I would not round the answer. So as much non-rounding as you can do is great, right? The question might say round to 4 decimal places or something like that, but I would just leave it in my written work, right? Making sure you round properly, right, to whatever number of decimal places. But at least this way I can look back and I can see, okay, I just rounded improperly or something like that, right, if I have the entire number. Okay, so remember, we have a binomial distribution, NP, which in our case, if we plug in those values, how can I represent this? I have a binomial with 5 trials and the probability of success is 0.56. That's not, we don't need to write it like that, but I did want to highlight that that's all the information that we need in order to answer this problem, right? So what's the mean and the standard deviation of this distribution? We said that mu is n times p, right? N is 5 and p is 0.56. Maybe I'll do them side by side here. 5 times 0.56. Well, 5 times 0.56 is 2.8. This is what we call the expected number of successes, right? And if I reformulated this, instead of asking you what the mean was, right? What if I asked you, okay, what's the expected number of successes in 5 weeks, right? Then you would take your 5 and multiply it by the probability of success, which is 0.56, and then it would get you to 2.8. Now, don't worry, because the mean is just an expected outcome. So it doesn't actually have to be one of the outcomes. And so if you're thinking that, then that's good, right? But the mean can be something between 2 outcomes. Okay. So the mean is the expected number of successes, and doesn't need to be one of the outcomes. And this is kind of where it gets a little bit weird, is because what we're saying is that, okay, if I look at many, many weeks, right? So 5-week intervals, and I consider many, many, many 5-week intervals, then on average, I would expect to have 2.8 increases per week. Okay, and so that's why we're allowed 2.8. It's not for this individual number of trials, it's for many, many repeated numbers. And you don't have to worry about that, but I know that that's one of those things that can be confusing in the beginning. Okay. And so sigma is the square root of NPQ. Sigma, remember, is the standard deviation, and that's the square root of 5 times 0.56. And even if we only have this information here, right, the binomial part tells us how to find the mean and the standard deviation, right? And so that's how we found, we know to use these formulas. And that's on that formula sheet that I gave you. 5 is your N, 0.56 is your P, but that means I also have Q, right? 1 minus 0.56. And so that's going to be 0.44 because we've already used it and shown it. So I can just jump right in. So then 5 times 0.56 times 0.44 is 1.232, but then I have to take the square root of that and puts me at 1.109954954. Good. Okay. Great. So now, right, what I said was, okay, if we have a mean and a standard deviation, remember, those were one of those things that we needed in order to use the Z-score formula and the Z distribution and the Z table and all that fun stuff, right? And so now we've got this segue into the normal distribution. And in fact, we have this approximation of the binomial distribution. So what I want you to imagine is, what if you didn't have a computer, right? Because that would make it easier. You didn't have a computer and you wanted to find not just 5 weeks, right? What if you wanted to look at 52 weeks? Very reasonable, right? The whole year, or maybe 200 weeks, right? How would you do it? How would you find the probability of at least 100 weeks? Well, no matter how you slice it and dice it, you would have to look at 100, 101, 102, 103, 104, 105, all the way up to 200. And without a computer, that just sounds like torture, or a special kind of calming math exercise, I guess. But it's not for me. I don't want to do that, right? And so even I don't want to do that. And so what's been developed is this normal approximation, okay, to the binomial. Okay. So we're going to talk about the normal approximation for the binomial. So when the number of possible outcomes is large, right? So if you have a large number of trials, right? So for example, consider consider 200 weeks instead of 5, right? And then I'm going to say find, but this was the example, find the probability that X is greater than 100. No matter how you slice it and dice it, that's going to be a lot of individual calculations. Okay? And so what happens is we can use the normal approximation to calculate binomial probabilities. Okay? And so what we're going to do is we're going to use the mu and the sigma that we just developed as our mean and our standard deviation in our Z-score calculation. So remember, Z is X minus mu over sigma, right? And X is going to be the thing we want to find a probability associated with. So the outcome of interest. So in this case here, if we consider this fake scenario, right? then 100 would be the outcome of interest. And if I want the probability of X being greater than 100, then I need to find the area above 100, right? And so in this case, there, in that example. Okay. And then this inequality, what happens is if we're looking at many, many trials, then including 100 or excluding 100, so what I'm talking about is the less than or equal to, the difference between doing that is very, very minimal. So it doesn't actually matter anymore, especially for the approximation. So whether it's greater than or equal to, it actually is the same calculation. Okay. And so then we can use the Z table to find the probability. Now, I want to make a note of what I just said. There is a note, but then another note. Finding the probability that X is greater than 100 versus the probability that X is greater than or equal to 100. Uses the same I'll just say are the same if using the normal approximation. Okay. So one thing is we started off and we said when the number of possible outcomes is large, okay, well, how large is large, right? And so what we need to say is that when we can use the normal approximation to the binomial, as long as we expect at least 10 successes and 10 failures. Remember, we already know how to find the expected number of successes, right? Which is mu, which is the expected number of successes. Okay. And then if I have n and the probability of failure, and I multiply them together, then of course that's the expected number of failures. And what we say is the expected number of failures. And the rule that we're going to use, and of course it can change depending on, you know, what textbook you're reading, but overall, like some fields use 5, but overall we use 10 for the binomial. Okay, so we need to have at least 10 expected successes and at least 10 expected failures. Now, this type of assumption checking is going to come back to haunt us. So it's a good idea to really get in the groove of checking this assumption before you use the normal approximation. Okay, and so because it's going to come back in a different form, but same idea. Okay, so what we said here, when the number of possible outcomes is large, the question might be how large? Well, this is how we find it. Okay. So we're just making sure that I have at least 10 expected successes and at least 10 expected failures. What does that mean? It means that my smallest possible sample size, if it was a 50-50 split, would mean I have a smallest possible sample size of 20, right? So a very, very minimum sample size. But then what happens as P maybe increases from 0.5 and Q then decreases from 0.5, the further apart they are, the larger sample size, total sample size we're going to need, right? And N is the number of trials, but it's also the sample size, right? So we're accounting for that. If we have these extreme probabilities, then we're going to need to increase the number of trials that we look at, right? Which makes sense. if something is hard to detect, right? So if it's very rare for a fish to have some abnormality, then of course you understand that you're going to need to look at many fish in order to even see a fish with that rare abnormality, for example, right? And so we need to increase our sample size, right? And then so now we have a rule of thumb of when we can use the normal approximation. Okay, so let's see here. And crop this here. Okay. Suppose that Canadian Blood Services anticipates the need for at least 1,850 units of O-negative blood for a particular region this year. Okay, very reasonable, right? And this can happen, and it does happen, right? So it estimates that it will collect blood from 32,000 donors. Okay, and only about 6% of people have O-negative blood. Okay, and so now, right, we are going to be able to find the probability of having some number of units, so some desired number of units of O-negative blood, right? Knowing how many donors we have, right? 32,000 is what they kind of, from previous years, they have a pretty good idea of how many donors they're going to have. And also, what's the probability of someone having O-negative blood? Okay. And this question, again, just kind of holds our hand a little bit. And so I'm going to, instead of answering the questions and then trying to answer the questions again, I'm going to do this. Maybe not so huge. What is a success in this case? Right? A success is someone donates blood and they have O-negative blood. So success is O-negative blood. Or a donor has O-negative blood. Maybe I should write that. A donor has O-negative blood. Okay. What are N and P in this case? Well, we have to be careful, right? The 1850 is how many units they need, right? But that's not how many times they try to get O-negative blood, right? The 32,000 is how many times they try to get O-negative blood, right? And each donor either is O-negative or not O-negative, right? Which is the majority of us. Can't remember what blood type I am. Should probably know that. But that's okay. The probability of success then is 0.06. Okay. So imagine if we didn't know about the normal approximation to the binomial, imagine trying to actually solve this, right? In fact, we're going to try to figure out what's the probability that they meet this quota, right, of needing at least 1,850 units of O-negative blood. Okay. What's the mean in the standard deviation? Well, the mean is N times P, which is 32,000 times 0.06. Let's 32,000 times 0.06. So I'm expecting 1920 donors to have O negative blood. That's good, right? Because I know I need at least 1,850, right? So now I am expecting more than that, but what's the probability of having enough, right? And so maybe I'll do these side by side so they don't take up so much space. Sigma is the square root of NPQ. So the standard deviation is the square root of 32,000 times 0.06 times, oops, I want to say 0.94, but let me just check. 1 minus 0.06. I don't want to leave anything to chance here. Dink. That's good. So now multiplying that through 32,000 times 0.06 times 0.94. And then don't forget to take the square root. Sigma is 42.48293775. Okay, good. So now we know the mean and the standard deviation. What's the next thing we're gonna do? Crap. We're going to set up the formula, and you can try to do it, but the reason I ask you to just set it up is because it's not going to work. Our calculators can't show the number, and it can't do the calculation for the choose function. So to set it up, though, we can do that. The probability of getting exactly, right? And so exactly 1,850 is the probability that X is 1850, which is going to be, okay, I know my N, I know my P, I know my Q, and K is going to be 1,850. So now I'm going to say that this is 32,000, choose 1,850, and you're welcome to try it. In fact, I'm going to try it on Desmos, but I don't think it works. I'm going to go to the choose function, 32,000, 1,850 is undefined because it's way too big, right? And so it can't do it. There's way too many options. And so times 0.06 to the power of 1850 times 0.94 to the power of 32,000, right? To find the number of failures, 32,000 minus 1850. 30150. Okay. Calculator can't solve, right? It's way too big. Imagine, right? What do we have? We have a tree diagram of 32,000 layers, and we're asking it to find, okay, how many ways can I have exactly 1,850, right? Even calculators can't handle it. Okay. We didn't even spend any time asking ourselves whether this was a binomial, and that's probably because I'm a little bit pressed for time here. But one of the first things we should have asked is this a binomial situation? Will I be able to use this as a binomial, right? And so let's just incorporate those checks. First, if it's a binomial, right, I have two possible outcomes. Which are O negative or not O negative. and I have fixed probabilities, right? P is 0.06 and Q then is 0.94. The only thing we need to say is the P, but can throw in Q too. Okay, so the normal approximation then requires that we have enough expected successes and failures. So the normal approximation conditions, maybe I'll formulate it with a question mark, just like I did before. Well, I need to have n times p, which in this case is 32,000 times 0.06, which we already found was 1920. And I'm going to just put a check mark. It's greater than 10. And maybe I'll reverse those. Because the check is it greater than 10? Yes, it is. A lot greater than 10. There are two ways that we could find the expected number of failures, right? Remembering that this is the expected number of successes. And the expected number of failures we can find by taking n times q, which is 32,000 times 0.94, which is 32,000 times 0.94, which is 30,080, which of course is also more than 10, check. Or, and maybe I'll do, I need a different color, orange. Or 32,000 minus the expected number of failures, right? And maybe I should do n minus n times p is n times q, right? N minus the expected number of successes must be the number of failures, right? 32,000 minus 1920 is 30,080, right? So it depends, whatever you prefer. I like to stick with just multiplying the probabilities, but just understand that you know how to solve these, right? And looks like I'm out of time, but I think that's a pretty good thing, actually. Give you some time to work through it on your own. And I'll make it part of the video for tomorrow. But therefore, we can use the normal approximation to the binomial. Okay, so the question that we're going to answer is, how likely is Canadian Blood Services to meet its need of at least, right? And so let's just have at least 1,850 units of O negative blood. And so you know the mean, you know the standard deviation, you know the value you're interested in an outcome from. So now all of a sudden you have a Z-score question that you can answer. Okay, so even though it feels weird, you know how to answer this question. So what I want you to do is try it, and then it'll be at the beginning of the video for tomorrow. So try solving on your own. for next day or for Friday, which is in a video. Always. Okay, I'm all out of time and I'm sorry. I hope you have a really, really great reading break. And I hope that you get all the things that you hope to get done. And then see you after that. If you have any questions, let me know. Otherwise, I'm going to stop this recording.